Okay, so I got a few more identities to review with you because you have seen them before. Before we get started into 5.1 fundamental trig identities, cofunctions. We introduced those in chapter 4, and cofunctions, what are they? Give me an example of two functions and two trig functions that are cofunctions. So there's going to be a sine of some angle, and then the cosine of some angle, tangent, and that's somehow related to cotangent. We've got then secant and cosecant. What's trig a study of? Not just right triangles. Angles and right triangles. So there is some angle, and then once we have that angle drawn, we draw its reference triangle, and that reference triangle is a right triangle. So all of trig, no matter what you're working with, somewhere behind the proof of whatever it is you're working is a proof founded in a basis of right triangles. So there's 180 degrees inside this triangle. 90 are made up of the, well, right angle. And that means that these other two angles have to be what? If this is theta, what's the other angle measure? It's supposed to be acute, but it has to be not just acute, but less than 90. Actually, it has to be complementary. You have to do some kind of calculation from 90. So if this is 90 degrees and this is, say, 20 degrees, this other angle has to be 70, right? Because the other two acute angles have to add up to 90, so that interior sum is the fixed 180 degrees. So the other angle is a complement. Now I'm going to write these identities in terms of radians, but trig is a study of rotation and right triangles. A right triangle has a 90-degree angle. The other two acute angles, therefore, by default, or by the sum of the interior angles, must be complementary. So when are cofunctions equal? Complementary. So, and we broke that down more specifically, more defined, more explicitly in chapter 4. I'm just reminding you of it now. But sine of theta is equal to the cosine of pi over 2, if I'm talking radians instead of degrees, pi over 2 minus theta. And you can move these expressions around and have sine of pi over 2 minus theta is equal to the cosine of theta, and that will still work. So these cofunctions are equal when the angles getting put into those cofunctions are complementary. And this is in orange, sort of like the mathy way of writing a statement of complementary angles, either pi over 2 minus theta and theta, or of course 90 degrees. Now, you also have properties that deal with the even and oddness of your trig functions. With an odd function, the check that we talked about in chapter 1 was for odd functions which are symmetric to the origin, opposite numbers in, opposite numbers out. So when you look at something like the sine of theta, well, what if you're comparing sine of theta and the sine of negative theta? What happens when you plug opposite angle measures into the sine function? What's that parent function for sine look like? What does the graph of sine of x look like? What's the sine of 0? 0. What's the sine of, I'm not going to put any scales on this, but what's the sine of pi over 2? 1. What's the sine of pi? 0. And so, because we've already learned this, so this is just a rough sketch of what the sine function looks like. Is that symmetric to the origin, or is that symmetric to the y-axis? The origin is that 180 degree rotation. If I were to take this, if this were a piece of paper and I were to put my finger on the origin and spin the paper around 180 degrees, I would have the same picture. All the numbers on the x and y axis would be upside down, but it'd be the same picture. That's opposite numbers in, like the sine of pi over 2 is 1 and the sine of negative pi over 2 is negative 1. Opposite numbers in, opposite numbers out. Your sine function and most of your trig functions are actually odd functions. So the sine of theta and the sine of negative theta, opposite numbers in, opposite answers out. So the sine of negative theta is the opposite of the sine of theta. That is coming from the fact that the sine function is odd. It's symmetric to the origin. What reciprocal function do we make from sine? What's the reciprocal of sine? Cosecant, right? So the opposite of cosecant of theta is going to be equal to the cosecant of negative theta. Tangent is also an odd function. So the opposite of the tangent of theta is equal to the tangent of negative theta, or the opposite of theta. Cotangent is also an odd function. So negative cotangent of theta is equal to the cotangent of negative theta. And the only two trig functions that are even are the cosine function. So your theta, your x-axis is theta. What's the cosine of 0? 1. What's the cosine of pi over 2? 0. What's the cosine of pi? -1. And so if you kind of just sketch this out or just picture what that cosine function looks like in your head, that's a function that's symmetric to the y-axis, which means it's even. What's the cosine of pi over 6? Square root of 3 over 2. What's the cosine of negative pi over 6? Still square root of 3 over 2. That's just a numerical example. It's not really a proof, but opposite numbers in, same answer out. That's an even function. So cosine is even, which means the cosine of theta is the same as the cosine of negative theta. And the reciprocal function of cosine is secant. So the secant of theta is equal to the secant of negative theta. But if you see you have that 180-degree rotation, and you would get the exact same picture, that is an odd function. That is symmetry to the origin. Cosine and secant are the only two even trig functions as parent functions. We've got the sine of theta is -3/4, and we're being told that the cosine of theta is greater than 0. We want the other 5 trig functions. So sine, tangent, yada, yada, yada. How would you figure out the other 5 trig functions? Knowing that the sine of theta is -3/4 and the cosine function has to be positive.
Did you draw a picture?
Oh my God, like everything we did in chapter 4 was based off of a picture. What are we going to have to do to draw this picture? Determine
The sides, like y and r?
Yeah, and where are we drawing this angle? Is it in quadrant 1, 2, 3, or 4?
Oh, so it's in quadrant 4 because the x is positive and y is negative?
Jumped right to it, yeah. So the sine of theta is y over r, and you have a negative ratio. R is never negative. R is strictly a distance. Your point on the terminal side of the angle is from the origin. So for the sine to be a -3/4, that means that y has to be negative, and that happens in quadrant 3 and 4. Cosine of theta is going to yield an x over r ratio. And if cosine is greater than 0, then x has to be positive, which means you have to have an angle in quadrant 1 or quadrant 4, and the overlap like quadrant 4. So we have an angle in quadrant 4. So there's theta. There is our reference triangle with a 3 for y, a 4 for r. And now this is where the picture comes into play. That is a movement down. And when you're moving down into quadrant 4, your y movement, I'm labeling this as a negative length for the right reference triangle, but that's really technically not right. But that's the way I like to work it out and show it. That's a -3. We're going to have to do a little bit of what to figure out the other leg? So we have x squared plus 9 is equal to 16, and x squared is equal to 7, and then x is equal to the square root of 7. And then without, the work is all done, the thinking is all done. Now that you have the picture drawn, you can just, just look at the picture to say, well, then the cosine of theta is square root of 7 over 4. The tangent of theta is negative 3 over square root of 7, and then just continue on writing out your remaining 3 trig functions. I would like to simplify the expression tangent of x cosecant of x. Can we do any algebra to simplify this? When asked to do a proof or asked to do some kind of simplification, the first thing you should jump to are your most powerful identities at your disposal. Right now, the only thing we have are these 3 Pythagorean identities. But these all involve powers of 2. Our expression doesn't have any sort of second degrees or powers of 2 or exponents of 2. And then your building blocks. Remember that sine and cosine build the other 4 trig functions. Sine and cosine are straight off the unit circle. They're like the most fundamental trig identities that we have, or functions that we have. They make the other 4 trig functions. So can I write tangent in terms of sine and cosine? Yeah. What's tangent of x? Sine of x over cosine of x. What about cosecant? Cosecant's a reciprocal of sine. Oh, okay. So we have an expression that doesn't simplify at all, but if we write these trig functions in terms of sine and cosine, what happens? Yeah, the common factors of sine cancel out. You have 1 over cosine of x, which is secant. Nice. This is actually a matching problem in the book. I'm just presenting it to you like a simplification problem. The sine squared x secant squared x minus sine squared x. Simplify that expression as much as you possibly can. Take a couple of minutes. I'm looking for only one term, only one trig function, maybe even getting down to as simple as a constant. It might even be a number, like 2. As you're doing these problems, what's one of our favorite words in math? The F word, factoring. Factoring helps simplification very, very often, and it's very powerful, and it should be the first thing you're looking at. Also, once you start seeing powers of 2 show up in trig proofs or in simplification problems, your Pythagorean identities have powers of 2 all over the place. So, not guaranteed they're going to be useful, but a lot of times they will be. So, factoring is reducing number of trig functions, reducing powers, canceling terms. That usually happens when you have an opportunity to factor and cancel or reduce. So don't go into sine and cosine too quickly. Is there any opportunity to factor, to do any kind of factoring here? Is there any opportunity to employ one of your Pythagorean identities in here? If there is, that can help you get to the answer much quicker. So those of you going into sine and cosine immediately, that will get you to the answer, but that is not a best first step when doing simplification. We do it often, but it should not be the first thing you do, the first thing you think about every single time. You didn't do anything to reduce the power. You got to keep the power, CC. Nothing, no wait. Nothing wrong with powers of 2. Did you do anything to get rid of it? No, you didn't. You just got rid of it. You just dropped it like it was nothing. But it's something. What did you do first? What did you identify first that you have in common with these 2 terms? You didn't factor an x out. What did you factor out?
Oh, sine.
Oh my God, they both have a sine squared, 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 sine squared. Both of these terms have a sine squared, right? So since these two terms both have a common factor of sine squared, this would in algebra 1 or 2 would be called factoring a monomial out. Both of these terms have this common factor of sine squared x. So you're going to factor out that sine squared x, and left inside, of course, sine squared x times secant squared x divided by sine squared x is secant squared x. And then you have a minus sign. Sine squared divided by sine squared is 1. And what is secant squared minus 1? What's secant squared minus 1? Okay. No, don't help her. So at this point, we've got a secant squared x minus 1. There is a Pythagorean identity that involves a secant squared. One of your three Pythagorean identities is tangent squared theta plus 1 is equal to secant squared theta. Now we're not proving this. We've already proved it true, so I'm just going to manipulate its format, subtract both sides by 1, and get tangent squared theta is equal to secant squared theta minus 1. Well, what is secant squared minus theta? Tangent squared x. So we can do substitution and replace secant squared x minus 1 with tangent squared x times sine squared x. And that actually is not going to simplify any farther. If you were attempting to continue to simplify this and look for some kind of additional cancellation, we have sine squared x times tangent, which is sine, over cosine. But going from a power of 2 to a power of 4 isn't really going towards that idea of being simpler. So because this is going to go up to a power of 4, I would just say stop and take this as your answer. Nice job. Take a moment and simplify this for me. We've got the cotangent of pi over 2 minus x times the cosine of x. Simplify that to, either a constant, a single trig function, and I want the angle left in your final expression to only be x. I don't want to see pi over 2 minus x in your final answer. All right. When you start seeing like weird looking angles like pi over 2 minus x or a 3x or things in the future, like whenever you see a sum or difference of angles, you're going to want to basically like rewrite that so that there's not a sum or difference of angles. So cotangent of pi over 2 minus x, pi over 2 is like 90 degrees, right? It's a radian version of 90 degrees. 90 minus x, that kind of sounds like what? A complementary angle. Tangent and cotangent. Cofunctions are equal when their angles are complementary. So cotangent of pi over 2 minus x is equivalent to tangent of x times the cosine of x. So do a little substitution with one of our identities. Tangent of x is sine of x over cosine of x times cosine of x over 1. There you go. So how are we doing? Is this stuff making sense?
Makes sense after you explain.
That's a very good answer. I like that. And that's kind of like where we're going to be at for a while. We're going to go from not having a clue to I can watch something be done and follow those steps to understand what's happening. But because I can only give you ideas of what to do, like when you see powers of 2, start thinking about how factoring and Pythagorean identities are going to help. When you don't have that situation, maybe you just need to go straight into terms of sine and cosine. There's not a sequential set of steps I can give you for this next chapter of simplifying, doing trig proofs and solving equations. So it is going to take some of that experience of like, I know I can't do this on my own yet, but you know, only consistent practice will do that. So I'm glad you kind of like can follow the steps, and I'm not expecting you guys to come in tomorrow and being able to like, you know, do every single problem in your homework without, you know, hardly any effort at all. But, you know, understanding is actually kind of a good place to be at the moment. You want to review some factoring? Yes! Woo! We got 5 minutes left. 3 sine squared x minus 5 sine of x minus 2. If I asked you to factor this, what would you do? Does it ring a bell, look familiar? Talk about this for a second. How would we factor 3 times sine squared x minus 5 sine x minus 2? Tell me how to do it.
Well, you take a sine out of the first 2 terms. No, just kidding.
You could, but you're still going to have a minus 2 hanging out at the end that's not.
Yeah, well, we're worried about it later.
Yeah, definitely not. If I were to set this equal to 0 and say solve the equation, taking a sine of x out of just the first term and not doing any factoring with the negative 2 is not going to lead you to a result that you want.
Yeah, just kidding.
You want to try something else?
I don't know another option.
Okay, let me give you a different question. Let's go back to solving quadratics. How would you solve this quadratic equation?
Oh, is it the multiply add thingy?
I thought you didn't know how to do it.
Well, I'm just thinking.
All right, so what are you going to do?
You add negative 5. Is that it? Yeah. Add negative. No.
Something's adding negative 5, but what's the first step?
3 and 2 are multiplying.
There you go. So we're doing the product, the product of A and C. So 3 times negative 2 is negative 6. So we're doing A times C, and we're looking for, in step 2, factors of A times C that add to B, that add to 5. So we're looking for factors of negative 6 that add to 5, and these numbers are small enough. I'm not going to keep going. You just mouthed it. What is it?
Negative 6 and 1.
Negative 6 times 1. So negative 6 times 1 is negative 6, but these factors also add to the middle term of negative 5x, or the middle value of b. So we have 3x squared minus 6x plus 1x minus 2 equals 0. What do these two terms have in common? An x and a 3. So we're going to factor out your 3x, leaving you with 3 divided by 3 is 1. X squared divided by x is x. So we have x, and negative 6x divided by 3x is negative 2. Now you need to factor something out of the last two terms to make the x minus 2 show up. But you already have x minus 2. So what do you have to factor out? Because we are factoring by grouping, and you have to take something out of both the first two terms and the last two terms, and Cole's trying to help you. Not that I think you need it, but we're going to factor out a positive 1. It's just for mechanics. It's actually not going to change anything. X divided by 1, negative 2 divided by 1 is still going to give you x minus 2. Now you've got two terms that both have a common factor of x minus 2. So what can you factor out? X minus 2. So you have x minus 2 times what? So your x minus 2 is coming out of the first term. What's left?
Oh, 3x was 1.
And your x minus 2 is coming out of the second term. What's left?
1.
Okay, so you have 3x plus 1. Okay, so we're not really being asked to solve this quadratic. You will be in the future. I mean, like, this is why we're practicing this. Ultimately, we're going to factor this. Sine of x is an unknown, and x is an unknown. So it is the same thing. It just looks a little bit more complicated. But you just factored the problem. Bam! All done. Go do your homework.